So today I'm going to solve the max point on the line problem. This is a notoriously hard problem in LeetCode with a very low passing score or acceptance rate. You can see that only 30% of submissions have been accepted by people. And this is, I think, one of the top 5 most difficult problems on LeetCode that is frequently asked in interviews. So yeah, I just thought I would walk you through the solution for this problem, the optimal solution. So the problem is as follows. So you're giving an array of points. Every point is an area of 2 coordinates on the xy plane, and you need to find the maximum number of points that lie on the same straight line. And here's some examples. Here you can see you have 3 points. They all lie on the same line. So here the answer would be, the correct answer would be 3. But if one of those points would be maybe down here, the answer should be 2, because you have only 2 points here that lie on the same line, or you would have 2 points here that lie on the same line, or even here you have 2 points that lie on the same line. So the challenge is to determine which points lie on the same straight line. A naive approach would be to check, to pick 2 points, and you can draw a line between 2 points, and then check for all the other points that are given if they also lie on the same line as the 2 points here. But that would be an O of n cubed complexity. You have one loop over the first point that you pick, then you have an inner loop that loops over the second point that you pick to establish a line, and then you have a third loop that loops over all of the other points to determine if they lie on the same line as the first 2. So that would require O of n cubed time, and we can do better than that. So what we can do is we could just look at the slopes of these that lie between 2 points. So we could, for example, have an outer loop that loops over all of the points to pick the first point, then an inner loop that loops over all of the second points that connect the first to form a line. That would give us O of n squared runtime complexity. And then we just check if the first point, well, we calculate the slope between the first point and the second point. And then as we loop over the second points in our inner loop, we calculate all the other slopes that the first point forms with these other points. So let's say if we look at this example, we pick this point, we calculate the slope between those 2 points, we calculate the slope between those 2 points, and you can quickly see that only here in this example we have actually a third point that lies on the same slope, right? So we calculate this slope between those 2, and then this slope between those 2, and those slopes would be equal. So we now know about a line that has 3 points lying on the same line. But if we are picking this point, for example, and we loop over all of the other points, we will see that this point and this point lie on the same line because they have the same slope. You can see that this point and this point and this point and this point on the bottom right lie on the same line. So now we've actually found a line where 4 points lie on it. So yeah, so this is the idea of the algorithm. One inner loop to loop over the first point we picked, one outer loop that loops over all of the first points we pick, and one inner loop that loops over all of the second points we pick. We calculate the slope, and then we just need to count how many slopes are equal. And we have to do this for every first point that we pick, and we remember which was the maximum count during all of our looping. So I'll just write down the runtime complexity. So we have O of n and time, and you will quickly see that we only need linear space as well, because we need to store all of the slopes, right? When we pick one point and calculate all of the slopes for the other points, we need to remember all of the slopes in order to be able to count how many of them are equal. So O of n squared time, O of n space, and so this will be our outer loop. We're just going to loop with an I over the index all of the first points. I'll just call them x1, y1 points I. So this will be the first one. And now for the second loop, we actually have to only loop over all of the points. I think that, yeah, we should be able to loop over all of the points that come after our point. I think, yes. Because if we calculate the slope from this point to that point, once we reach that point, we don't have to calculate from this point to that point, right? It doesn't matter because we've already calculated that that line, how many points lie on that line between those 2 points. But the runtime complexity will still be n times n. And so here we have the point with the coordinate x2 and y2. And j, technically we could also say -1 here, but nobody does that, so we'll just leave that out. And yeah, so now there's going to be an edge case. So here, for example, you see that these 2 points have the same x value. And I don't know if you remember your math, but if you want to compute the slope of a line between 2 points, the slope equation is equal to the y coordinate of the second point minus the y coordinate of the first point divided by the x coordinate of the second point minus the x coordinate of the first point. So this could give us a division by 0 when we compare these 2 points. So what we're going to do is we're going to have a little check here. So if the x values of those 2 points are equal, you're just going to say that our slope is we just say it's infinity. Otherwise, we know that we can calculate the slope. So what do we do now with the slope? Well, we said we have to remember the slopes. So we need a data structure to actually remember the slopes. I'm going to use a dictionary for that. And for convenience, I'm going to use a dictionary from the collections framework. In this case, the default dict. And so what we do is we initialize it like this. And we say that this contains integer values. Now the nice thing about the default dict is that when we try to access a key element, an element in here, and it doesn't exist, we get back 0 instead of a key not found error. So that is the convenience that this default dict provides us instead of using the regular Python dictionary. So what we now do here is we just say count slope. We just increase the count by 1. Now, so here we pick the first point, and now we're looping over all of the second points and calculate how many points that form a line with the first point have the same slope between the first point and the second point. So in the end, if you look at this example, we would have 3 points, right? But the value in our count would only be 2 because we pick the first point and then we increment it every time we find another point. So it would be 0. Then when we pick the second point, it would be 1. And when we pick this one, it would be 2. So we found 2 additional points that form a straight line with the first point. But the number of points is actually +1. So so what we have to do is, well, we have to somehow use this information to update our maximum number of points on a straight line. And so far we don't have a return value. So let me just specify that real quick. I like to use the variable result because then it's quite clear that this is where the final solution will be. So inside the inner loop, I'm just going to update the result. So the result is going to be equal to the result the maximum between the result and our count slope, but +1. And that's pretty much it. So yeah, now some people start to try to solve this problem where they put like some data structure outside here where they say counts and then they count, well, they create a large data structure that stores all of the slope for all point combination, but it's not really necessary. You only have to store them for all point combination with the first point that you've already selected. So that's why you get away with creating this data structure in the inner loop. that means you reduce the space complexity from something like n squared to n, and you just have to update the final result. So let's run this. And it works just nicely. So now there's one more thing. When you solve LeetCode problems, you always have to check for edge cases. And so far I didn't do that. I should have done this very early. So the number of points could be 1, and all points are unique, right? So this is another important thing. If the points were not unique, this would probably not work like it does, right? Yeah, it wouldn't, and I wouldn't know right away how to solve it. But that could be another exercise that you could try. But what if the points array only has length 1? Well, in that case, we execute the inner loop, but the outer loop. But the inner loop will never do anything because its range is essentially 0. So the result will also be 0, and we get a wrong result. So for this edge case, we have to set result to 1, because we know we're at least going to get 1 point, so it's safe to set result to 1. 1 point is always going to lie on any line that is defined by that point. So once again, it looks nice. Now I submit it. And yeah, you can see that actually works. So yeah, so there you have it. That's it. This is a really nice thing to know. It's one of the hard problems on LeetCode. It pays to know how to solve this. If you get this in an interview, I think you should just remember, what is the slope formula? How do you deal with when the slope is undefined? In our case, we just set it to infinity. And the trick of using a data structure only in the inner loop and update the result as the maximum inside the second for loop.